A-level core. Radians. In everyday life we measure angles in degrees. There are 360 degrees in a circle, so 1 degree is 1/360th of a circle. This way of measuring angles goes right back to the Babylonians, who often used 60 as a number base because it divides by 2, 3, 4, and 5. Defining the internal angle of an equilateral triangle to be 60 degrees leads naturally to the result that the angle in a circle is 360 degrees. This is because 6 equilateral triangles fit into a circle. This has many other useful consequences. Many important angles are whole numbers when we use degrees. The internal angle of a square is exactly 90 degrees. The internal angle of a pentagon is 108 degrees. For a hexagon the angle is 120 degrees. For an octagon it is 135 degrees. The diagonal of a square is 45 degrees. Although degrees are very useful, dividing a circle into 360 degrees is quite arbitrary, and for more advanced mathematics it is preferable to use a different unit of measure. Radians are a better way of measuring angles in mathematics. This diagram shows a circle of radius r. If we draw an arc that is the same length as the radius, then the arc will subtend an angle of 1 radian at the center of the circle. That is the definition of a radian. We know that the circumference of a circle is 2 pi r. This means that the arc will fit around the circle 2 pi times, so there are 2 pi radians in a circle. 2 pi is approximately 6.28. Since there are 360 degrees in a circle, this means that 2 pi radians is equivalent to 360 degrees, so 1 radian is equal to 360 divided by 2 pi degrees, which is about 57.3. It is useful to know the radian equivalents of some common angles. We know that a circle of 360 degrees is 2 pi radians. This means that the angle on a straight line, 180 degrees, is pi radians. A right angle is pi divided by 2 radians. 60 degrees is pi by 3 radians. 45 degrees is pi by 4 radians. 30 degrees is pi by 6 radians. We can do a similar calculation for area. We know that the total area of a circle is pi r squared. We can find the area of a sector of angle 1 radian by dividing the total area by 2 pi. Simplifying the expression gives the area of a 1 radian sector as a half pi r squared. So what are the advantages of using radians? If we plot a graph of sine x using radians, it turns out that the slope of the curve at the origin is exactly 1. We won't prove that here, it is a topic for another video. But this is the basic property that make radians such a natural unit for measuring angles. If we were to measure angles in degrees then this would no longer be true. In radians, 1 full cycle of the sine wave curve occupies a distance 2 pi, about 6.28, on the x-axis. In degrees, a full cycle occupies a distance of 360. Changing the unit stretches the curve along the x-axis by almost 60 times. As you can see, as we stretch the curve it changes the slope of the curve at the origin. The slope is no longer 1. In fact it is 2 pi divided by 360. Having a slope of 1 at the origin leads to some other important equations, which again we will not prove here. The limit of sine h divided by h, as h tends to 0, is 1. If we measured h in degrees, that limit would be 2 pi divided by 360, which isn't quite so elegant. We can also show that the first derivative of the sine function is the cosine function, and that the first derivative of the cosine function is the negative of the sine function. Finally, we can express the sine function as an infinite polynomial, called a Taylor series, like this. There are equivalent results if we use degrees instead of radians, but the factor of 2 pi divided by 360 appears in the equations. This generally makes things a lot less clear and simple. If you enjoyed this video, please subscribe or visit graphicmaths.com.